Hello everyone, my name is Cheong Song from the Department of ICT Convergence Engineering at Gangnam University. Today, I will present on the topic VDSR for improving image quality in low and high frequency domains. This study was conducted to address the limitations of the existing VDSR model and propose new possibilities for image super-resolution technology. The presentation will proceed as follows. First, introduction. Second, related works. Third, proposed method. Fourth, experimental results. 5, conclusions and future directions. Super resolution is a technology that converts low-resolution images into high-resolution images. This technology is widely applied in various fields, such as medical image restoration, enhancing the resolution of satellite images, and improving the image quality of consumer cameras. Among existing studies, VDSR is a particularly significant model that has substantial improved SR performance. The key features of VDSR are as follows. Leverages a deep neural network structure to learn more complex patterns, and it utilized the residual learning technique to learn the difference between high-resolution and low-resolution images. In the field of super-resolution, input images are used after being converted from the RGB channel to the YCC channel. In the YCC channel, the Y channel contains brightness information, which makes it efficient to use only the Y channel for restoring fine structural details in images. Additionally, calculating all YCC channels increases the number of parameters and the computational load for the model. By focusing solely on the Y channel, the model's complexity is reduced, allowing it to concentrate more efficiently on the details required for SR tasks. Residual learning, as employed in VDSR, has also been adopted in this approach. This technique involves learning the difference between the target value and the output of the model's neural network. By doing so, it accelerates the learning process and enhances the efficiency of the model. The existing VDSR model has a significant limitation. It does not distinguish between different frequency bands in the input image during learning. Low frequency bands contains information such as overall color and brightness, while high frequency bands include details like textures, edges, and fine structures. Due to these distinct characteristics, SR in low frequency band can result in blurred images, whereas SR in the high frequency band may produce images lacking sufficient edges and details. These limitations become more pronounced in images where the characteristics of specific frequency bands are dominant. To address this issue, we propose a model that separates images by frequency bands and processes them independently. By learning each frequency band separately, the proposed model overcomes the shortcomings of VDSR, which struggles with SR performance in specific frequency bands. Our proposed model consists of three main steps. First, frequency separations. The input image is separated into low frequency and high frequency components using Gaussian blur. Second, a low frequency image is generated by applying Gaussian blur to the input image. The high frequency image is obtained by subtracting the low frequency image from the original input image. Gaussian blur is implemented using a Gaussian corner, which is a filter matrix. By applying the Gaussian filter to the original Y channel input image, the pixel values of the image are replaced by the weighted average of the surrounding pixels, resulting in a smoothing effect on the image. If the original input image is divided into low frequency and high frequency bands, each of the separated frequency band images is then input into the VDSR model for independent learning. In the low frequency band, the model focuses on learning the overall structure and color, while in the high frequency band, the model learns to restore textures and details. The independently learned results from both bands are then simply summed to generate the final resolution image. This process emphasizes both frequency bands, helping to overcome the limitations of the original VDSR model. The performance of the proposed model was evaluated through the following experiments. The datasets used were SET15, SET5, and BSD100, which are the same as those used in the original VDSR. The experiments were conducted on Google Colab with an NVIDIA 8100 graphic card, trained for 80 epochs. To objectively assess and validate our proposed model, we used peak signal to noise ratio known as PSNR and structural similarity index known as SSIM. For the test images, we selected images from the dataset that clearly exhibit distinct low frequency and high frequency characteristics, as shown in the table above. For images with strong low frequency characteristics such as the airplane image, and strong high-frequency characteristics such as the flower image, the PSNR and SSIM scores have increased by 1.5 to 2 levels compared to the original model. Using these PSNR and SSIM metrics, we can conclude that our proposed model outperforms the original VDSR in terms of performance, particularly in specific frequency bands. Throughout this study, we have demonstrated that frequency separation can improve the performance of the VDSR model. In future research, we expect to achieve even better performance by introducing more diverse frequency separation techniques. Additionally, we are planning to explore model lightweighting for real-time processing and the integration of other deep learning-based image restoration technologies. Thank you for listening.